My name is Helen Forgas. I'm Professor Emerita at Monash University in Melbourne, Australia. And today I have the pleasure of chairing the session for the Emma Castelnuovo Award winner, and I'll say a little bit about Kaye in a moment. But let me first remind you what the Emma Castelnuovo Award is for. It recognises outstanding achievements in the practice of mathematics education. The award was established in 2013 by the ICME Executive Committee to reflect the ICMI principles to the development of mathematical education at all levels and to promote the reflection, collaboration, exchange and dissemination of ideas on the teaching and learning of mathematics from primary to university level. So this year, as announced at the opening ceremony, the award went to Professor Kaye Stacey for her more than 40 years of research-based development and implementation of innovative and influential contributions to the practice of mathematics education. Her groundbreaking portfolio of books and papers, curriculum and assessment materials, and teacher preparation programs developed with diverse collaborators from around the world have had remarkable influence locally and internationally. I now invite Professor Kaye Stacey to address you.
Thank you very much, Helen. It's lovely to be introduced by someone who I've worked with over the years. So, when I was asked to write the abstract for this talk, they said to make it anonymous so no one could guess who it was. So I hope it's not too anonymous, but I thought that the title of the talk is, I've been trying to reflect on sort of some of the strategies that we've used to take our research and our teacher education into, to really make it, give it an impact on school mathematics. So as a university researcher and a teacher educator, we're not in the sort of mainstream of education in the schools where everything happens, and so we really do need some strategies to, to make an impact. So I think that the first thing I thought I'd do is talk to you a little bit about my mathematical background and why I love mathematics, and just give us a little bit of a setting of how it is. Now, these are the strategies that we're going to talk about during the lecture. I'm not going to go through them one by one, but I hope that they might come up and you'll see that the sorts of things that I'm trying to do is to think about how we really use strategies like sometimes if there's an educational fashion, and we've been doing some research on something, it's really good because that's a way of getting into practice. And there are many other strategies, and we'll talk to them as we go through the lecture. Okay, so first of all, I'll tell you a little bit about my mathematics. I always loved numbers, but then I loved geometry when I got to secondary school and calculus. I did my undergraduate maths at the University of New South Wales. I got a scholarship to Oxford to do a PhD in number theory, and where I married my lovely husband Peter, who's still in the audience after all these years. And then I'm going to tell you a little bit about my PhD problem. So it begins with the Kepler conjecture, and I think this starts with Sir Walter Raleigh, who was a sort of English buccaneer entrepreneur. He was travelling in the 1600s by that sort of boat over to the Americas and I guess, trying to get riches to take back to Europe. And of course he needed a lot of cannonballs, and so he asked his friend, who was a mathematician, Harriet, according to Wikipedia, to give him a formula for how many cannonballs there are in a stack. I suppose they're very, very heavy and you can't take them out and they're on your ship and everything. So Harriot thought about it for a while and then he wrote to his friend Kepler, and Kepler is down here. And Kepler thought about it for a time, and by 1611 he made a very important conjecture that the best way to stack cannonballs or any other sphere would be in that sort of hexagonal pattern that we know really well from, say, stacking oranges and things. And that's the Kepler conjecture. I've got this picture to remind you that we're not talking about stacking cannonballs just in that sort of way. This is endless going on. If we go, no boundaries, what's the densest way? Okay, so Kepler made a conjecture. Gauss, in 1831, was able to prove that Kepler's conjecture, if everything was lined up. It wasn't proved otherwise, and for 400 years. So we have Hales and collaborators. You can see that his collaborators include humans and digital proof assistants, and they proved the theorem. I did a little tiny bit in the middle of this from Gauss's problem about lined up close packings. Oops, I keep pressing the wrong one, sorry there. In here, I was up in 7 dimensions there. So I want to tell you that there's some things about mathematics that I think this problem really explains. But just before I do, this is a picture of Emma Casanova from the internet, of course, and this was the only picture about her work. And it's interesting that this would be a close packing of 2-dimensional spheres, circles, but of course she's taking them out to make this beautiful Sierpinski gasket. Okay, so the sorts of things that I think there's really comes from, think about mathematics. It is such a significant part of culture. That's wonderful, isn't it? That 400 years people can work on the same project. There are so many elegant structures and so many surprising discoveries. There are so many unexpected and important applications. Now, one of the important applications for packing spheres is actually to making error-correcting codes, which you wouldn't expect, and it doesn't work. For that, you need to be thinking about that problem in many, many dimensions. And so it's a very interesting thing about mathematics that you get sometimes it's abstraction that is what makes it powerful. It's difficult for students, but that's what makes it powerful. And the generalisation is where you get the applications. It's not just from the first part of a problem. I think the other wonderful thing is even a problem like this that has taken 400 years to solve has many smaller, easier problems that people can solve at all times. So, for example, I just had a look at the number of spheres in different sorts of packing, just in cannonballs-like packings, and those are patterns that children can find from about the age of 10. So that's some of the wonderful things I think there about mathematics and its teaching. Because I was interested in problem solving, I began my career working with Susie Groves with problem solving, and we were in teacher education, and we felt that what we wanted was to give students confidence to tackle non-routine problems. So we used lots and lots of different problems. You can see some problems on the screen there that are completely pure mathematical, and you can see some applications to car parking, to shop putting, and other things. But what we did as a strategy, which proved to be very good, we had our student teachers, then we took our student teachers to school, and they taught students in small groups, so children in primary school, and then we went to the schools and worked with teachers. So we had that 3-phase thing, and what I realised from that is that it is incredibly important for people in teacher education and in any sorts of mathematics education to really understand how students think about things. And so that was a wonderful legacy of that work. So, our problem solving, we then worked, we put it into books. I wrote a book with Susie, another book with John Mason, and we went to the ICME 5 Adelaide, and that's a picture of me there, taken by Peter and our youngest, the youngest of our 3 children, at the ICME excursion day 40 years ago. You probably can't recognise me. But I'm not one of the ones in the middle. Okay, so we didn't know, because we were just working in a teacher's college, and there wasn't the internet or anything. We didn't know that the NCTM had said that problem solving was going to be the theme for the 1980s. And so a lot of our impact in this case, what have we done is worked with children, we'd got good problems, and suddenly our strategy for impact at that stage was just luck. So we always have quite a lot of serendipity there, but we did have some books, we had some great problems, and we knew how children worked on them. And so I think that was the key strategy that we used accidentally in our first our first area of interest. Okay, so then working in teacher education, we really had to work on the school topics that our student teachers were going to teach. And so this section is about the work that we've done that I call seeing mathematics through the eyes of learners. It's just such an important thing that I feel is the basis for all sorts of things. So I'm going to talk about some research projects that we've had attending to academic and practical things, and we've found that we can get good research money that way. We've wanted to share our research in different ways with teachers, and we've produced resources and other tools for teaching. Okay, so I've got 2 quotes here. The first one by Kierkegaard tells you what you already know, of course, is that you have to, if you want to teach well, you have to take the learner from where they are. And the second one by a popular writer, Stephen Jay Gould, says that when you look at the world, you can't help but look at it through your own spectacles. So you have to look through the spectacles of your mind. So because we're all professionals, we look at the world of mathematics through our spectacles. But children, those little pink glasses, they're the spectacles that children look through the world. So I think that what the main aim of teacher education has to be is to make bifocal spectacles. So you have to take the way the children look at the world and the way you look at the world in a mathematical point of view, and you have to combine them and be able to see them together so that your student teachers develop children's spectacles that they can just put on when they need to understand the world from the student's point of view. And I find this quite a helpful metaphor. So we want the knowledge of students' maths, all of that in those pinks. And so teachers have to be able to take off their professional spectacles of maths and put on the spectacles of the children. So we've done this in lots of different ways. For example, we began with a lot of work on algebra. And what we wanted to do there was, in one part of our work, looking at how students transition from learning arithmetic to learning algebra. This is a very simple little problem. And I'm not going to show you many examples, but this one, Mark and Jane share $47. Mark gets $5 more. That's Mark up there. And how much do they each get? Use algebra. Okay. So what did students do? A lot of them get it right and they use algebra, so that's wonderful. A lot of kids just guess by numbers. A lot of children work it out in a really good way. And you can see this person here, Brenda, she split the 47 into 2 halves and then she made Jan give $5 to, half of $5 to Mark. The common error would be $5. And then she said, oh, gee, they've said use algebra, so she put an X and a Y on the end. And that's very common. You can see clever children doing this for algebra. And often it's even a little bit more stark like that. So Wiley here, he's telling us, take the 47, take off the 5, split it in half. You notice he's actually got a slightly different method to Brenda's method. And then take that $5 that you took away and give it back to Mark. So what we've got is all sorts of kids who are writing algebra. We ask them to do algebra, so the algebra's just sticking, or Mark sort of put it at Wiley has put it at the beginning. And so I think this gives us quite a lot of insight into the sort of transitions that students need to make. The other thing, of course, is that they keep using X for all sorts of things. So Tim, for example, writes X plus 5 equals X, and you ask him what X is, and he said, well, X is Jan's X, and X is Mark's X, and then he'll use X for 47, and then he'll use it for 42. And that's because he's thinking about arithmetic. And so there's quite a lot of, I've just got some characteristics of student solutions there, but I guess what you really see is some of the obstacles that we wanted our student teachers to know for algebra. And basically, I'm not going to go through all of this, but what there's a big transition that you have to make from how you solve problems in arithmetic to how you solve problems in algebra. In other words, teachers have to have those two spectacles, have to still be able to see the student, the world, mathematical world through the students' arithmetic glasses and then through their other ones, and then help students make a transition. Okay, so our main messages for teachers in this work is algebra is a new way of thinking, and knowledge of how students think about algebra can help teaching, for example. Okay, so for that, the work in algebra, we'd really basically done research articles and articles in teachers' journals. Later on, we started to work on decimal notation with lots of my students and colleagues, and we decided that this was the beginning of the digital era, in a sense. And so we were able to take the research that we were doing on decimal numbers and to treat it very, very differently. So one of the things that we did was to make a CD, which at the time we even got special money for the university for putting our work on the web and making a CD. So it was quite a new thing. And it was fantastic. We found that there were all sorts of things that we could do for our teacher education and for teachers in schools that we hadn't been able to do before. For example, we took our research interviews and we made case studies from them. And you can see the 6 case studies that we made for the decimals, our decimals CD. And up here you can see my lovely colleague Vicky Steinley in an interview. We put those interviews onto the CD, and our student teachers could look at them. We've also got a picture here of a computer game that we wrote, and on our CD you could see students using our computer game. Not real video because you couldn't download it over the internet, but little cartoons really. The other thing we did about this was, instead of using a research interview, we really cleaned them up and made what we thought were textbook cases of students. They have to be easy enough for people to understand. So, a lot of people think about using research for teacher education, but instead, I think it's much better to clean it and use textbook cases that show things very dramatically. We had a lot more success with our student teachers doing that. Okay, and those are the other thing that we did in the decimals test. We had a test to see how students were thinking about decimal notation, and it proved to be very successful. Lots and lots of teachers asked us for the copies of the test. So we realised that that was a way of getting things into classrooms and out of research, because what we wanted was that teachers to actually be able to see how their own students were thinking about things and to match them up to one of our case studies. Right, so here are our main messages from the decimals, and in particular, at the end, a very, very well-designed test can give us a lot of information into students' thinking and was very popular with teachers. So we thought, well, if we can do that with the decimals, we could do that with all sorts of things. So we're trying to think here of how to get research knowledge out of our library, picture there, off our CD and out of our conference papers and into the classroom. And so we thought that the tests were the way to do it. And that's when we devised our smart test system. And so that's exactly what it was. We were trying to think how we can give a tool for teachers to use actually in their classrooms there. So a fully online test, we had you see the description there, but what we're aiming to do is to report to teachers on every student in their class on how their student is thinking about a really, really specific topic, a little short test. We were operating at the time when we did this long before there was good technology in schools, and that's one of the issues about this sort of research. You have to work in advance of the field, but there are various obstacles that you're never quite sure how it's going to work when technology catches up. So I'm just going to skip that one. This is, as well as our decimals test, we have many different other sorts of tests. So this, for example, is a test on reflection, and what students have to do is to pick up a dot, which I think I could do there, and then they just got to put it here where that reflection would be, or they'd have to put the dot for this one over here, and they have to pick a fish there and put it over there, the right one. So we have many, many different sorts of short, little, easy items for children to do, very, very well researched. Behind this needs to be pretty complex programming. So, for example, for this fish, every single one of those rectangles there gives us different information that we can build into the diagnosis that we've got for every student. And the important thing to know about that is that you never send a human to do a machine's job. And a lot of this sort of thing, this technology of teaching really is a machine's job. It's not reasonable to ask a teacher to do it, but you can do it by a machine. Okay. So that's the sort of thing that we do for our smart tests. We've got reports on every student. We take the research results that we know, for example, looking at any one of those tests, and we try to put them into a few easy words for teachers to understand. It's not an accurate description of research, but it's the best that we can get in a few things, and we also add it with teaching suggestions and other things there. So I think that's one way that we've really been able to try to get the research we've had into the classrooms by capturing the teacher always wants to teach their students in the best way they can, and we want to give them easy individual information about the individuals in their classroom. Okay, so a few issues in the manufacture of bifocal spectacles. I think we've probably had a look at those. I think that second dot point, that teachers really want to know. They don't want to know research, they want to know how it applies to their students. I think that's really a key thing. The other thing that really is important is that items which reveal thinking often have very poor statistical properties. And so they, for example, would never appear on NAPLAN because they won't fit the NAPLAN measurement models. So you have to do something different with those sorts of items. You can't expect tests, standardised tests, to give you the sort of data that you need to really understand your student thinking. Okay, I did want to talk then about some other aspects of our work. So for that, the previous part, we've been looking at how we try to take research on students' thinking and putting it into the hands of teaching. I think now I want to talk a little bit about what we're trying to do with the mathematical power of technology. I think this is the challenge. When people look back in 300 years, they'll say, those were the people who first had to deal with computers and automated calculation. Wonderful opportunities, and the mathematics curriculum really needs to change. When I talk about calculation, of course, I don't just mean numbers. I mean statistics, I mean calculus, I mean finding the area of shapes, I mean graphing, all sorts of things. I'm talking about all of that just as computational calculation. Okay, so right from the 1970s, and it was interesting hearing Barry talk about the Casio calculators, people expected these sorts of things of calculators, 4-function calculators. That they'd make mathematics more useful, they'd improve students' enjoyment of mathematics. We don't know really if that happened. And they wanted to increase students' motivation to learn, so high goals. And they thought fewer tedious calculations. That has certainly happened. We have a lot less calculations that are truly tedious. Enabling greater use of real-world examples, which we all hope will still happen, and also being able to teach topics better. That wasn't seen at the beginning, but it was found very early. So, for example, Susie Groves and I worked on a calculator project early in the 1990s to try to get young students using calculators a bit more. And there was wonderful work, particularly on how students could use calculators to scaffold their learning and to explore. So this one is a lovely little picture drawn by Kylie. I've forgotten actually whether she was in the first year of school or in grade 1. So she was counting backwards and she drew this picture, 8, 7, 6, 5, 4, 3, 2, 1, 0 is the ground, and then she drew her underground numbers. And she'd only just really learned to write those numerals as well as anything else. So we very quickly found it's wonderful for exploring, and wonderful also for scaffolding learning. So the sort of scaffolding we had, again, say counting backwards, students were able to hear and see. We think that's really still underused in schools, and it's so interesting that it just not seems to be moving for so many years. So I think it still remains quite a challenge there. So we've got that, teaching students mathematics, the important things, it changes what mathematics is important to learn, long division, not important. Using technology well needs lots of mathematical understanding, especially for formulating problems and for checking the reasonableness of results. And we've got many pedagogical opportunities. So we did that 4-function work just at the time that technology was getting more interesting. So what's happened since then? We got graphics calculators and we got from scientific calculators to graphical calculators to computer algebra calculators. And this affected the main substance of teaching mathematics in secondary school. What do you do with graphing? Things that took a long time in secondary school have been really affected. You have a tool that students can use if they understand the mathematics. And so through this for this sort of research, I had a wonderful group of people at the University of Melbourne, Linda Ball, Robin Pearce, Barry McRae and many others. And we worked pretty carefully in many ways with the State Authority for Education. And this is a map that David Lee Lancaster, a wonderful person from the Victorian Department, BCAA, we've got a map there of the sorts of technology change. So until about, 1977, we had logarithms and slide rules. Then we got a long period into the 90s where we were using scientific calculators, and that was pretty well easy to do. For the graphics calculators, because they could graph and do statistics and things like that, there was a fair bit of work that needed to be done, and they were more complicated machines. So we were particularly the people on my department who also worked for the exam setting. They did a lot of experimentation of what would the impact be on the school exams, because that is what determines so much there. And so we developed this strategy here of having a time when technology was permitted but it wasn't necessary, so to give teachers a transition. We did that for graphics calculators. For computer algebra, it was much more complicated technology in itself, and very, very, very impactful on the actual, on the questions that could be asked and what was expected of students in Year 12. And so for that, instead of just having a short time, we worked with the Victorian Curriculum Assessment Authority, and we got a pilot project in here which carried on for several years. So we had 3 years of our pilot, and then just a small number of schools trying to work out how we were going to run a senior secondary system with important exams at the end, based around calculus and algebra and all of those things that were really, really affected by the computer algebra. And so it took us, we took there some years. For these years we had these were parallel, so we ran 2 courses separately, and then since 2010 we've used CAS. CAS has been assumed that students could use it in all of the exams in Year 12 in Victoria. So what we can see, I think the strategy there was because we had research projects that paralleled what was planned to be happening in the exams. So for our research, we basically looked at curriculum change, we looked at assessment change, and we looked at how we could help the pedagogical opportunities. Okay, so curriculum change, we did learn to be very, very careful. Can't change very much, very often, really. So the assessment change was really very, very large, that there were so many questions that couldn't be asked anymore. And so the examiners and the people on our team were thinking, Peter Flynn, other people there, were thinking exactly how questions could be changed so that we could still test mathematical understanding and not have questions that were still validly assessing mathematics, given that students may be using the algebra on their computer, on their CAS, for example. There were other issues like being equitable to everybody. because, we wanted to make sure that people could afford, relatively expensive technology. We also did quite a bit of work on the pedagogical opportunities, because we think that most teachers, most of the time, if you ask them what they want to use technology for, they don't say curriculum change. What they tend to say is they want to teach mathematics better. And so it's the pedagogical opportunities that we thought were quite important. Just to give you a little bit of an indication here, changing the classroom social dynamics, a lot more sharing. So these pictures, we've got those girls there talking together. Mine says such and such, what does yours say? That sort of thing. Here we have a teacher, these students working on a computer, and they're looking at the output and discussing it together. So I think one of the strategies there is students do have a bit more confidence because they've got a personal thing. So that was useful for us. Here's another example. There's a picture of Linda and Robin and Roger and Inge, a visitor from Taiwan. And this example, the work we did on the changing didactic contract in mathematics, when you use technology, suddenly you've got a lot more ways of actually solving a problem in a practical way. And so we call that the explosion of methods. And the students can become a source of information instead of just a sink. And they can share and talk about things. So we've got a picture of this girl. You can see we did this now a long time ago because she's using an overhead projector there. And she actually is sharing her work with a confidence and a way that she wouldn't have done before, and she might have used a solution method that was different to somebody else's because of all the opportunities that you have. So there's quite a lot about the classroom dynamics that can change that in a way that teachers liked. Okay, so I think that part of our work has made a very direct impact on the teaching mathematics in Victoria. I think the CAS is securely embedded, always a little bit scary. And I don't know what's coming, because I just wonder what is going to happen next, say, with the AI. But anyway, we feel that's been a very worthwhile project, or series of projects over 20 years. Okay. Now, the other thing that we can do, I guess another theme that we really have done a lot of work on, is to make mathematics useful for everybody. Like, really, I don't think enough students leave school saying, yes, mathematics is going to be useful in my life. They might say, I need it to get into such and such. But we really do want every student to know that mathematics is useful. One of the wonderful things you can do, for example, with technology, is to try to bring the real world more into the classroom. This was something that was noted when the first 4-function and scientific calculators were there, and we still need to do more on it. So let's just have a look at some of these. I think I've just thought about 3 different ways that you might do that. One is just strengthening the concepts by connecting them to real-world phenomena. And this is already, I think, well established. I've taken the photo of this, a picture of this. This is a Desmos activity that's been available for quite a long time. And we've done perhaps 20 years now. I think really it should be much more common by now. But we can think about how to, just by using photographs, for example, in this one, you can see videos of a basketball, and the students have to find the parabola to see if the basketball goes in the hoop. And the idea there is that they're going to be learning how to manipulate ax squared plus bx plus c, those parameters a, b and c, so that they get a parabola that matches these, and to see if it goes in the hoop there. The same with this one. This is water coming out of a hose. We've used that one for trying to teach students about how the shape of parabolas, the different forms of parabolas and those sort of things. So ordinary mathematics, but with real-world examples. So another way, I think we can use mathematics to really use the real world to motivate mathematics. And this is one that, this is a scissors lift. We love scissors lifts. Just think about all these parallel lines. I think everybody knows a scissor lift, you know, it's very low, and then it goes, takes a person up to change a light bulb, or take a photographs. The other scissor lift you saw, that person was taking photographs at the Ballarat Air Show. This one we use to teach geometry. It's a resolve lesson. And the aim there is for students to think what geometry makes this work. And so you have to think, well, what's the important thing? Now, I think for scissors lifts, probably the most important thing is not to tip this man out. Okay, so you have to hope that this is going to be horizontal, and you have to keep him horizontal all the time. And so there's a lot of work on quadrilaterals in Year 8, and so we can use this one to show students how the properties of the quadrilateral, in this case they're rhombuses, really keep him horizontal all of the time. So you can think about that one for homework, but what we do there is we've got a video or image, or it might be a real thing. We use a GeoGebra, a dynamic geometry model, and the idea is for students to analyse the geometry by looking at the motion, seeing what's necessary about the motion, and then why does it work? And I'm sure you've already guessed that the diagonals of a rhombus intersect at right angles. So that'll keep you horizontal. Pretty fantastic, really. Okay, and I can't show you the GeoGebra but if you pull this in, you can see this thing going up and down, so students can actually work, they can measure with that, and it's a really good mathematical model that they can work on. That's what it looks like. If you pull this point in, you can see those ones go up. Okay, we've done quite a lot of those for Resolve. Folding umbrellas. Why does your folding umbrella fold? Well, the answer is because there are parallelograms in there. So again, the same sort of idea, taking the properties of quadrilaterals, which so many things depend on in the real world, and using them to motivate proof, mathematical proof. Let's prove that this is right. Okay. Another aspect of the real world has really been the teaching of mathematical modelling. So we've, again, working with Resolve and working this time with the Shell Centre, we were working on units of mathematical modelling, and the sort of thing we were able to do there was to say, looking at why do big vehicles cut the corner, how much they cut, how much space do they need. Say if you were designing a roundabout, how much space would they need? And again, we found something that's been very successful is combining the various different sorts of models, using various different sorts of models to get the abstract and to really highlight the mathematics. So in this case, you can see that those lines are just wet wheels on the scooter, riding around in a circle to make some real measurements. And then we have geometry models of many different things. So the sorts of important things about mathematical modelling we have with that, we want to see why a big vehicle, cuts the corner. Let's look at a scooter first, very small vehicle, and then we can look at, then we can eventually give it width. We can see what happens and do some measurements, do some predictions. Okay. Now, my favourite little model for mathematical modelling is this one by Singe from 1951. What you have to do for mathematical modelling is dive out of the world of reality into the world of mathematics, take a swim, and then in his words, you climb from the world of mathematics back into the world of reality, carrying the prediction in our teeth. And there's lots of other models of mathematical modelling, but but I think that's a nice one. But what that shows you is that's mathematical modelling really for solving real-world problems. And, oops, what is that? Good. In the last couple of years, was working with Hugh Burkhardt, who sadly has passed away, and Daniel Peed, to look at teaching of mathematical literacy, trying to make mathematics useful for everybody. And I think as well as those sorts of models of mathematical modelling that we've had before, we need something a little bit different. That's our book, and I'll just tell you that there is a special ICME discount of 35%. That's the code there, if you want it. CHLTFM. I hope it works. Right. When we were writing this book, we went through all sorts of different real chapters on all sorts of different parts of life. We looked at climate change, we looked at epidemics, we looked at money, we looked at making decisions at risk. And what I noticed towards the end, and what we all noticed, was how many mathematical models people use every single day. So this is the website of choice, which is a Australian consumer magazine. And this is their mathematical modelling for what a good washing machine is. Okay, you look at the dirt removal, you look at the rinse performance, you look at the gentleness, you give them scores, and that's the mathematical model. So the goodness of washing machines is measured by a mathematical model, and that mathematical model has got properties, and students could understand them. We do lots and lots of work on linear functions in schools, but usually it's only got one, maximum two variables. That's a mathematical model, that one, that people would meet, and all sorts of rating systems are mathematical models. If you go for a bushwalk, you might see how long it's going to take. That's probably a mathematical model. Okay, that's from the mathematical modelling things. Students, we've got the Olympics are coming up. How do you measure how good someone is at running? Well, you just see who comes first. That's pretty easy, I think. I'm sure it must be more complicated than that, but sounds pretty easy. But there's a lot of complicated sports, and there's an absolutely beautiful lesson from Enrich on mathematical models at the Olympics. It's about how you score the decathlon, where you have to combine things where you have to do things in the short time and things that you have to do as far as possible, like a pole vault, running a hurdle race. And that's really, there's lots and lots of mathematics in that measure. As we did the other chapters, we came across so many other species diversity. We hear about species diversity is increasing, decreasing, satisfactory to build a dam or something. But you have to measure species diversity, and that is a mathematical model accessible to Year 12 students. All of these other things that we came across, why do you square the height in metres at the bottom of the body mass index? We talk about social inequality. Social inequality is growing in Australian schools, terrible. But how do we measure social inequality? That's another mathematical model. So I think to make mathematics useful for everyone, a new thing that we really need to do is not so much, as well as teaching people to make mathematical models, we also need to make sure that all of our students know that role that mathematical models are playing in their everyday lives for all the sorts of things. Almost the measure of almost everything that's not a physical quantity is some sort of mathematical model. And students need to understand that, and they need to understand the consequences of things being a mathematical model. And they need to think about how they could design good measures themselves. So I think that's something that's come out of writing our book more recently that I think will try to perhaps change the way I start to think about making mathematics useful in the world, as well as teaching people to do these things. We also need to teach students to understand how mathematical models, for example, actually work in their lives. So to know about modelling, not just how to make models. And I think that's one of the things that's affecting mathematics teaching all the time, isn't it? That we have to, perhaps more and more, we're having to teach about mathematics rather than actually teach what we would have thought of the basic skills of it. I think it's a very big challenge that's going to stay with us for some time. Okay. So what I've tried to do is to show you some of these strategies that we've used over the last few years to try to take our work from teacher education and university researchers and make them useful for schools. And I've done it with so many wonderful colleagues that it's always been fun. And I hope that you also enjoy doing the same thing. So thank you very much.
Rather than push Kaye not to finish her slide presentation, she warned me that she might go a little bit over time. I thought I'd let her take her time and complete the presentation, which I'm sure you all found very, very worthwhile. I think it's quite obvious from what Kaye has presented today, and I think she's done an amazing job in summarising 40 years of work, why it was the choice of the committee, the Emma Castelnuovo Awards Committee, to award Kaye Stacey the award at this ICME conference. So I'd like you again to thank Kaye for all the innovative work that she has done, research-based work, curriculum development, resources for teachers, the whole gamut of what we on the committee expected of a winner of the Emma Castelnuovo Award. So please thank Kaye.